Hello, I'm Timothy Nguyen from the PVA project, and this is Dummies guide to position, velocity, and acceleration. First off, let's look at a graph. You've probably seen one of these before. This simply means that at time t, the graph's position is at point st. Simple enough, but sometimes graph can have a negative aspect, whereas a point above the x-axis is considered to have a position forward of the start at x equals 0. A point below the x-axis is considered to be a position behind that starting point. Now let's define some terms. Distance is the change in position. It's basically how much you traveled. It's like what a step counter would track. On the other hand, displacement is change in position from the starting point. It's where you are relative to the start. It's basically like looking at a map and drawing a straight line from start to finish. If you think of it as a distance between two legs of a triangle, where displacement is the hypotenuse, the distance are the legs of those triangles. Let's look at another graph. At time t, the distance traveled is 5 meters. The displacement is also 5 meters from that start. But look at this. The dude traveled 10 meters forward and walked back to the start. In 10 seconds, the distance traveled is technically 20 meters. 10 there and 10 back. But the displacement is 0. Now let's define velocity. Velocity is the displacement over time. From start to time 5, you traveled 10 meters. Therefore, you traveled 10 meters in 5 seconds, or 2 meters per second. Now, if you travel there and back in 10 seconds, technically you went vroom, but your velocity is 0. Nothing changed about your displacement. You started at 0 and you ended at 0. Speed is different though. Speed is distance over time. You traveled 20 meters in total, there and back, and you got it done in 10 seconds. That's 2 meters per second in terms of speed if you maintain that pace throughout the whole time. And note that because speed essentially tracks how much you're moving distance, remember, it can be a negative number. Otherwise, that Fitbit might be wrong. Okay, pause. Remember what a slope is? Rise over run, right? Change in y over change in x? Well, golly gee, in a position graph, the distance and displacement is on the y-axis, and time is on the x-axis. Essentially, isn't the slope of a position graph the same as velocity or speed? Distance over time is that definition of speed. Aha, big brain. And finally, acceleration. Imagine this. You're at a red light and it flashes green. You hit the gas pedal and go from 0 to 60 on the speedometer in 6 seconds. You just accelerated 60 miles per hour in 6 seconds. Now, imagine there's a red light. You hit the brakes and go from 60 miles per hour to 0 in about 10 seconds. You just decelerated 60 miles per hour in 10 seconds. You accelerated negatively. That's essentially all it is. Acceleration is a change in velocity in a given amount of time. That's usually shown by meters per second squared. Pause again. Change in velocity over change in time. Change in y over change in x. Slope. The slope of a velocity time graph is acceleration. You can slope position graphs twice to find x. Okay, when the position is constant in place, velocity and acceleration are also zero slope. When the position is progressively going forward in that forward direction, velocity is positive, but acceleration is 0. When position is speeding up, as in speeding up in a general direction, velocity has a positive slope, and acceleration is essentially just shifted up, but is still a 0 slope. Also, you can sort of think of it like this. When there's a curved position graph, there is going to be a lined graph, and there is going to be a certain 0 slope on the acceleration graph. When there is a line position graph, there's going to be a 0 slope on the velocity graph and also a 0 slope on the acceleration graph. All right, big boy time. You'll need to know what derivative and integration is. Come back when you know it. Awesome. We found out earlier that acceleration is the slope of velocity is the slope of position. In other words, derivative. Derivative of position is the velocity. It's that simple. I already showed you how to analyze a graph in order to identify the different aspects of PVA on that graph. But what about equations? Well, it's pretty simple. All you have to do is apply derivative rules to find velocity and acceleration. As long as that first position function is twice differentiable, you can find velocity and acceleration from that equation. Now, how do we go backwards? We do antiderivative. If you have an equation for acceleration, just integrate the area under the curve to find change in velocity. And you can do it one more time to find displacement. Remember not to forget the c in that equation, and remember again that areas under the x-axis have to be subtracted from that total positive area under the curve. And maybe it's harder to grasp this concept of integrating position, velocity, and acceleration. I've had trouble with it in the past too, but let me blow your mind. On the acceleration time graph, what's on the y-axis? meters per second squared. Now what's on the x-axis? Time in seconds. When you find the area under the curve, aren't you multiplying that y by the x? Or in other words, that meters per second squared by seconds? Aha! Meters per second squared simply becomes meters per second, which is velocity. So basically what we're saying is the area under that curve is basically going to be velocity. Now, some of you might be asking,
Bro, imagine if there was like another derivative of acceleration. Wouldn't that thrice differentiable equation be like crazy?
yeah, it's a jerk.